existence of supercuspidals and exactly when self-dual exists and self-dual cuspidals exist. So this is what we were doing. So we proved a proposition, um, and that proposition, and then to prove the theorem for simply connected groups, we required, we left out some cases which we'll handle today. So what was the, let's recall the hypothesis we are working with. So let me know if is this visible, the screen?
Yes, yes, it's fine.
Okay, good. So the hypothesis was that G, our reductive group, has no factors of type 2aq, 2akq, where k is equals to 2 and q is equals to 2, k is equals to 2 and q is equals to 3 comma 4, or k is equals to 3 and q is 2 3 5, or k is equals to 4 and q is 2 3 4 5. So there are two parts of the hypothesis. Sometimes we need just one, sometimes we need two. A is required for existence of delinguistic cuspidals, and B is required for self-duality. So when the field is very small, then we cannot handle some factors of type special unitary groups. But for if the field has cardinality larger than 5, then none of the results are conditional. So let me restate uh, the special case of the general theorem, which is uh, so assume that G is simply connected. So then we were trying to prove that GF admits irreducible cuspidal representations, and if G satisfies hypothesis 1A, then GF admits irreducible Deligne-Lustig cuspidals. Moreover, if G is also satisfies this the other one, hypothesis 1B, then the following are equivalent. G has no factor of type an, where n is even. GF admits irreducible self-dual cuspidals, and then the third is the same thing, except that which are Deligne-Lustig. Um, so the theorem says that uh, you always have for simply uh, so the general theorem says that you always have cuspidal representations. What we are proving now is the special case, which is assuming G simply connected. So it always admits cuspidal representations without any hypothesis on G or the field. Delinelustic cuspidal um, requires a hypothesis that uh, it does not have for a field of order 2, you don't have SU2 uh, factor. And for for the existence of cell duality, you are ruling out some more factors when the field is less than small. And then self-dual exists if and only if self-dual cuspidal exists, if and only if self-dual delinealistic cuspidal exists. So this is what we are doing, and we were doing the proof. Recall that in the proof, in the
So,
second
Manish,
lecture, yes.
so this k equal to 1, there is no hypothesis. I mean, like for SU2, there is no. So this is true for all Q.
So in k is equals to 1, there is only it's only SL. There is only you are in SL2 case,
Right.
not SU. So
Okay, okay. There is no twist. Sorry, sorry, sorry. Okay,
right, right, right.
okay, okay.
So recall that we did so we did a proposition where we said that if if q comma h is not equal to 2, h was a twisted Coxeter number, and h mod t is even. So t is the splitting field of G, a degree of the splitting field. Then last time we have shown that we can find a self-dual pair t comma chi, where t is Coxeter. Um, so we can find a pair or consisting of a Coxeter torus and a character of its rational points, which is in general position, and it's taken to its inverse by some Weyl group of element. And and then q comma h is equals to 2 comma 6. This consists of like 5 cases or so. They were handled by hand. um, 2 3 lines to each case. And then finally you um, so if h mod t um, is odd, then the result um, uh, um, was there. If it was sorry, it's if I h mod t was uh, even, then it was there. It was, we already proved it. If it is odd, then there were some cases uh, to handle 2dn and greater than equal to 4 odd. Um, and we proved 2e6 in previous lecture. So so in 2e6 we could not find a Coxeter torus, but we could find something very similar. We could find an elliptic torus with a cyclic Weyl group, and everything flowed pretty much like in the Coxeter setting. So uh, that was um, yeah. So that was lucky. It doesn't work like that in the remaining 2 cases. So there you cannot expect to find uh, that kind of elliptic torus with cyclic Weyl group in general. So the remaining 2 cases are more complicated uh, for odd. Okay, so there you have at least, but or the good thing is that you have a classification of elliptic tori of these groups. So I'll recall this now. So now the Um, okay, so let's for the moment assume that we have already handled these two cases. Then let's proceed to prove the theorem. So what remains to prove is that if you have factor of type A, if you have if G is of type AN and even, then it does not um, 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 admit self-duality. So the way you prove it is that you elliptic tori arise from elliptic elements of the Weil group, those with eigenvalue 1, and uh, and we know that in the type AN in the for GLN. So this let me record this fact. Elements of Weil group in AN are precisely Coxeter, and this is in Carter's book. This is proposition 23 there, and from this you find that for GL n plus 1 F, all cuspidals are and from this another you know thing in the literature, you find that um, all cuspidals of are of Deligne-Lustig type, and then there is a result of Din-Michel um, that the same therefore would hold for PGLN. For PGL n plus 1F. And so PGL n plus 1F has no um, uh, uh, irreducible self-dual representations if n is even. Um, so now for other isogenies, we can reduce using the following lemma. So the lemma, which we won't prove but just state, is that let F be, so this lemma is more general than the setting we are in at the moment. So let F be a finite or a non-Archimedean local field, and let zeta be a central, let me call this capital F, central F isogeny um, with the kernel K of odd order. So this is crucial, that this kernel is of odd order. Then GF admits irreducible self-dual cuspidals if and only if G prime does. So if the kernel is of odd order, then you can choose any isogenous group, and you can deal with any isogenous group, and the same result carries over for um, other isogenous G prime. So in particular, the simply connected cover will also not have subdual representations if PGLN plus 1 doesn't have. Um, so this covers the proof in the simply connected case modulo the two cases that we have left out, 2AN and 2DN. So now we go and give the broad idea of how we do that in these two cases. So we'll just sketch the broad ideas. So for that we need the classification of tori in uh, special orthogonal and unitary. So M even and UM. So let E over F be quadratic extension for each natural number D. Let ED and FD denote the extensions of E and F respectively of degree D, and let uh, this TD denote the kernel of the norm map. And now let G be the unitary group or non-split form special orthogonal group where M is even latter. If T is a maximal elliptic torus in G, then TF is isomorphic to this product of TDI, I is equals to 1 to R, where the factors uh, the sum of these degrees DIs is M. If G is unitary, we require all DI to be odd, and if G is orthogonal, then R must be odd. Okay, so all rational points of elliptic tori of these two groups, they look like this product of rational points of some smaller rank tori of some other groups, and the number of terms. So the degree of so this so the terms must be odd if you're dealing with special or orthogonal group. Okay, so now conversely, given any product of as above, there is at least one associated maximal elliptic tori. Torus. Okay, so now we have described how torus looks like, and for the purposes of this problem, the important thing is the action of the Weyl group. So the action of the Weyl group is as follows. So the action on TF of the TF. This is what we want to understand. So this is generated by the action of Galva EDI over E on each factor TDI together with those permutations uh, in the symmetric group of R, which give rise to odd TF via permuting factors. So, so your T is a product of certain TDIs. If TD appears certain number of times, then these factors can be permuted amongst each other. But if TD1 is not equal to TD2, then they cannot be swapped. So this is one of the actions of the Weyl group. One way in which Weyl group acts, and the other way is acting on the individual factor. The action on the individual factors is via the Galva group. So the these TDs are defined in terms of the field. So there is it comes equipped with the Galva action, and so that is the Weyl group action. So TD. So now notice that TD is isomorphic to the group of rational points of a Coxeter torus T prime in sp2d. The Weyl group of T prime in sp2d acts on this T prime f via Galva ed over f. So notice that the TD, when seen as a torus sitting inside sp2d, then the Weyl group uh, there is bigger. It's ed over f, not ed over e. So ed over e is indexed to there. So so the Weyl group action on this factor is obtained by restricting the Weyl group action um, to ed over e. We obtain the action on the factor TD of TF. Um, and this is a cyclic group, and the generator uh, acts by Q square. So this is how the tori in these two groups look like, and we just need these two groups, and then by certain tricks about isogenies, we handle all um, isogenies of uh, almost simple groups of this type. So I'll just sketch the main ideas. Uh, so suppose you um, um, your, your your torus had just two of these factors, tk times tk, and then you consider the character group of this torus, and then we use notations from our previous lecture. So the character group is denoted L. So then L will be a product of Lk times Lk, where Lk is the character group of uh, Tk, k greater than 1, k not equal to 3, we are assuming, if q is equals to 2. And now Lk is the rational points of a Coxeter torus of a symplectic group. And so there we know how to produce uh, um, an element Vk in Lk. So in the Coxeter torus setting, we know how to deal with situation. So there is an element Vk in Lk, which is in general position with respect to the Weyl group of sp2d, which is Ek over F of um, so this Vk generates a cyclic group, which is a prime number of order L, order L, and Q has uh, 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 order 2k. Q um, so the Coxeter number is 2k, and Q has order 2k. So L divides so it has order 2k, so L does not divide Q plus 1, because then Q would have order 2. So L does not divide Q plus 1. If K is even, then choose Vk to be conjugate self-dual, and let Vk prime to be QVK. If K is odd, let Vk prime to be negative Vk. So, let me just explain what I'm doing here. So Lk times Lk, in each of these factors, Lk and Lk, you can choose using your previous lectures ideas, uh, an element in general position and having order of the Coxeter number of uh, the SP uh, 2k. Um, but you want it to be general position in the group um, where uh, where L is being considered, and so it should not be an element where permuting the factor fixes the element. Okay, so you want the generators to be different in a way so that the while orbit does not have a fixed vector. Uh, when you permute the factors, so that's why we have to choose different generators, and still they should uh, continue to be in general position. Uh, so that is what we are trying to do. So if k is even, then you can choose this, and k is odd, then you can choose a negative vk, and that does the trick. So in either case, uh, vk prime is not in the orbit of vk under this galva ek over e. So vk prime um, is the right guy, is the self dual, conjugate self dual general position. So this is what we do. So this is the main idea in trying to produce a conjugate self-dual element in the characters of a torus, elliptic torus in general position. So let's see the illustration in case of SO2n. SO2n, where n is odd, k greater than 1. So choose maximal elliptic torus T such that TF is isomorphic to TK times TK times T1. Okay, so our while group of TF will act on individual factors, and it can also permute some factors. Which factors can it permute? Only the first two ones, because they are isomorphic factors. So it can permute the first two factors. Now we know how to handle the first two factors from the previous paragraph, and T1 we can handle independently. So uh, so that factor is not affected by these first two factors. So there is an element V in L that is conjugate self-dual in general position. Its while orbit lies in a subgroup of L of odd order. So the order of the orbit is something that we have to consider when we deal with amalgamating various factors. you so these choices one has to make carefully so that our center does not create problems. So that I'll come uh, actually now. So I sketched how you deal with special orthogonal group. Uh, so you can choose an elliptic torus with which looks like this, and which looks like a product of elliptic tori of smaller rank groups, and then in the smaller rank factors we can choose uh, our general position element, and we choose these elements wisely so that it remains in general position in the bigger torus, and then by construction it will be conjugate self dual. Um, and then in the special unitary group case, the torus, um, it's more complicated uh, to deal with this trick. So you have to have a lot more factors. So you have to pass to more complicated elliptic tori to make this same trick work. So now I sketch how does one pass to from uh, almost absolutely almost simple to semi-simple groups. So assume G is semi-simple and G tilde simply connected cover of G. So there is central K isogeny, G tilde to G, and let T tilde naught be the maximal torus of G tilde, which is contained in a Borel, um, and which Borel, and T naught its image in G, in G. So the simply connected cover, it is a direct a product of almost simple groups. It looks like this, and the maximal torus there is then a direct product of um, tori, restriction of scalars of tori of these smaller these factor groups, where ei over f degree ni extension. So likewise, for an elliptic torus, uh, T tilde of G tilde, you will have uh, uh, it will look like restriction of scalars of T tilde I, um, where So this is the pullback of elliptic torus T of G. Okay, so uh, we have this picture, um, and one would like to. So we have already dealt with handling factors. Now we want to glue them together. So we somehow want to use the information about factors to get uh, the information to get an element in L. So we know how to construct an element in L tilde. L tilde is the group of characters of T tilde. We want to pull it to L. The problem is this is not a surjection, and so you cannot simply pull back things, but you can pull back the elements we have constructed in a lot of cases. So the idea of the proof is that you reduce to the case where none uh, so if the factors that if you have fact if you have no factor which require this special handling, then you can show that the elements v tilde I in L tilde I can be pulled back to vi, and in the special handling case it just fails. So you have to reduce to the case using various lemmas about isogeny, so which I cannot detail in this lecture. So reduce to the case where G tilde factors of G tilde as types that require special handling. Choose V tilde I in L tilde I wisely. Um, which allow lifting to Vi in L, and then put V is equals to summation Vi. So this will be our candidate, the conjugate self-dual element in general position in L. So this requires some work, but the main idea is that you you pull back elements from the factors to L by making uh, right kind of choices. So then finally we have to go to, from semi-simple groups, one requires to go to reductive groups. Let Z naught, the identity component of center of G. Then there is a very easy lemma. Let tau prime be a representation of G mod Z naught F. Then tau prime pulls to a representation of GF. Moreover, if tau prime satisfies any combination of properties, of being irreducible, cuspidal, delinguistic type, self dual, then same holds for tau. So this is just Lang's theorem. So you have a short exact sequence, and so you get a long exact sequence. F, then H1, F, C0. And by Lang's theorem, you know that this is trivial. So GF surjects to Z mod G naught F, and then the remaining part is easily verified. So Z mod G naught is semi-simple, and so you can pass to the reductive case using Lang's theorem. So so this more or less gives the main ideas of the proof of uh, uh, the result in finite reductive groups. And now one has to, so the second part is lifting these results to p-adic groups. So there I need to talk about some notations. So I'll wait here to see if there are questions. Okay, if there are none, then let me continue.
Maybe I will ask you a question, Manish.
Yes, Dipendra.
These lectures have been a bit condensed, and even for me, I am losing a bit of track of it. Is it possible to quickly summarize what are the broad outline in 1 or 2
Okay.
minutes? What has happened?
Yes. Okay. So so we are trying to do existence of
Constructing a
cuspidals.
self-dual cuspidal representation.
Right. Constructing self-dual whenever it is possible, and proving that in other cases they don't exist. So showing exactly when they exist under some cardinality of the field hypothesis. So we try our luck with Coxeter tori, and so we first start with absolutely almost simple groups. We try our luck with Coxeter tori. We see that it mostly gives the results, except when H mod T, the twisted Coxeter number mod divided by the splitting field degree is odd. So in that case, so you are left with three cases there. Three cases are 2E6, 2AN, and 2DN, and odd. And 2E6, we
GLN
showed
also
in the,
will give you some problem, no? GLN and odd.
so GLN and odd, we prove that there are no self-dual representations. So that follows from the same
N odd and P
proposition.
odd. N odd and P odd.
And p odd, yeah, p odd. So
And on the
in
odd,
this,
there are no self-dual representations.
right. So because the elliptic tori are Coxeter, and the proposition that we proved in the last lecture, we showed that you know, you cannot expect things to work out from Coxeter tori. The idea is that the while group is cyclic of odd order, and so the you cannot do self duality by this group.
Right.
Um, so and so in and so so an factors are ruled out because gln ones don't admit when n is even, and then uh, the case of 2e6 was very close to the Coxeter setting. It's a coincidence that it just works out by choosing not Coxeter. So there you don't cannot get it by Coxeter, but properties with very similar things like Coxeter. You get a cyclic while group, and you can do the same thing.
But there are many more elliptic tori in E6, no?
Yeah, many more elliptic tori, but there is one decent guy who does the job with the cyclic while group and the more or less the same trick. So the uh, so there I explained in the last lecture that you can get an elliptic non-Coxeter tori for which like 80% of the proof works. And finally, we are left with these two cases.
In
2D,
E6. No.
no, 2E6 we covered, and
Okay.
we are left with two cases, the 2AN and 2DN cases.
Hmm.
And there is you just cannot get by dealing with an elliptic torus with a cyclic while group. So the while group will not be cyclic. It will be a product of cyclic groups. Elliptic tori will be product of tori of smaller rank groups, but product of Coxeter tori of smaller rank groups.
Hmm.
And the while group and uh, the the smaller tori are norm one tori uh, of certain field extension. So that I explained in this lecture.
Hmm.
And the while group acts on the individual factors of the tori by Galois group and by permuting these factors which look like the same thing.
Hmm.
So you can choose one generator. So they are Coxeter tori in smaller rank groups. So we can, by our Coxeter tori trick, we can put uh, figure out a self dual element in general position in the smaller rank group. But then there are many choices, and then and you cannot choose the same choice because while group allows you to permute similar looking factors. And if under permutation the element does not go to a different element, then it's not in general position. So you have to choose a generator wisely, and
So
and so that
if you, in your notation Tn, if you looked at T1 to the
yes,
power n, that may do the job for most Q, but not for all Q.
right. So this is the suggestion that you gave for UN. So it works for unitary groups when you just take T1 T1 T1, and then you just take QV Q square V and all, and you can do this for large enough Q. And
But by choosing the Ti appropriately, you can do it for any Q.
right. So you can reduce your hypothesis to leave out only very small number of these factors. So cardinality at most 5. You have to lose some of these factors in the hypothesis, because there you just cannot make the same trick work when cubex becomes very small.
You only look at the linguistic representations, or you look at more general representations?
Only Deligne Lustig for the cell duality. We are only trying to construct Deligne Lustig.
because they are cuspidal unipotents, etc., which may be
In
used
very
for.
small, so to reduce the hypothesis, sometimes we take cuspidal unipotent or some small rank factors. But um, but for gluing these together, we need we need we only most of the paper is only about the linguistic cuspidals. And the thing is, we want to pull it to p-adic setting, and from a pair s comma theta, which I'm just going to go to.
All right.
So
Good.
is this broad picture clear?
Yeah. Good. Good.
Okay. So now I go to the p-adic setting. So
And okay,
if
just to clarify that even in isogeny, there is some issue that when you lift a representation to a covering, it may decompose.
yes, so you may not be able to lift your the generators of factors in general, right? Because you know,
When you have
because
isogeny G to G prime, and you have a representation
yes,
of G prime FQ, and then you restrict it to GFQ, then this
right,
representation may be reducible.
right, and so in terms of these character groups, the L to L tilde, it's not a surjective map,
Yeah.
and you cannot simply pull back, you know, the things that we have produced in L tilde I.
Hmm.
Right. So in some cases you can pull back, and there you do pull back. In some cases you don't get to pull back, and there you have to, sort of get rid of those factors by specialized results about isogenies.
Hmm. You you prove the theorem for simply connected groups and then deduce it for the rest.
Yes, yes. We prove the theorem for simply connected groups, and we prove some lemmas about, what happens under isogenies. So one of the lemmas I stated in this lecture, that if the kernel is of odd cardinality,
Hmm.
then self duality here is equivalent to self duality there.
Right. Okay.
And so you play around, you choose right kind of isogenies, um, so that you can get rid of some factors by
But that is
using this.
not always guaranteed that the isogeny is of odd order.
It is not guaranteed. Yeah.
So, so
Um,
spin over SON, for instance, spin over SON, it's a degree twofold cover.
right. So in SON, the isogeny is so it's even, and it's an even isogeny, and but in this case, uh, uh, it does not trouble me, because
Because
uh,
anyway, you would have you deal with the SON or you will deal with spin.
so spin also. So the result is about spin, and from the spin we deal with SON, and from SON we derive spin, and so there is a two isogeny, but we handle that. Um, uh, so the cyclic group that we construct there, it is of odd order, so uh, it does not get uh, bothered by uh, the the isogeny. It does not get perturbed by two. So we are okay. We can lift from L tilde to L.
Yeah, under an odd order mapping, a self-dual representation restricts to something which
Sorry, yeah. So I am, yeah. Um,
something which has a self-dual component.
yeah. So we are in L tilde, not L tilde. So in the SO2N case, we from SO2n we want to pass to spin, and we take the inverse image of T in spin, and then the character group of T surjects onto the character group L prime of T prime with kernel of odd order. This surjection is equivalent with respect to the Weyl group action, and there the um, um, so the generator that we get, it does not get perturbed, um,
But
because
your theory doesn't work both for SO2n and spin group. Do you need to do something to deal with both, or it anyway deals with both the groups?
so the theory deals with all the things, but 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 so there are two steps. One is doing it for simply connected almost simple groups, and then passing to semi-simple groups. So even though in the almost simple groups we first do it for SON and then go to spin groups, and then we use spin to do the other isogenies. So that is the thing. So
Arguments cannot directly work both for spin and SON simultaneously by all the Coxeter elements and Coxeter tori and self-dual representations, etc.
so the argument for spin is not very different. It immediately gets derived from SON. It's just two lines. So yeah, so there it doesn't create a problem. So yeah, yeah. So I don't know if I can give the details right away.
No, that's okay. No, I just no, it's okay. Please go ahead.
Okay, so let me go to the p-adic group setting. So now F non-Archimedean, local, G connected F reductive F group, and then BG is reduced building. So now we recall some standard notation. So this is the stabilizer. Of X, and then G F X comma 0 is parahoric at X. Then G underbar X is the reductive quotient of parahoric group scheme. Special fiber of parahoric group scheme at X, and X is isomorphic to X comma 0 G F comma 0 plus. Okay, so let me explain this a little bit. So for each reductive group, there is a construction of what a polysimplicial complex, which is called the building. And what we are doing using is reduced building here, which I cannot explain right away. But, so um, so we are using the building of the semi-simplified form of G, on which G acts, and then to each point of the building you can associate parahoric group schemes. Then to to that point, you take the special fiber, and it usually is not reductive. So you take its reductive quotient. That is what we are denoting by under bar x. And then this special fiber reductive quotient has a property that um, the the it's a so the its f rational points is isomorphic to uh, parahoric mod the pro p part of it. So that's very important because uh, this is the route where we pass from the representation of finite group to representation of p-adic group using this isomorphism, the last one. And uh, so if you have self supercuspidal depths. So in the first lecture, I talked about what it means by depth. And if you have a depth 0 representation, then there is a result of Moore and Prasad, which says that there exists a point in the building such that pi restricted to g f x comma 0 contains the inflation to g f x comma 0 of an irreducible cuspidal representation rho bar of g under bar x f. So um, so this immediately tells you that if you have constructed a supercuspidal representation of g under bar x f, then you get a depth 0 supercuspidal of of the p-adic group. So I'll just record the statement then. GF has depth 0 supercuspidal representations. So there is not much to do in the proof. Now I'll go to um, uh, the notion of regular depth 0. So a depth 0 representation pi of GF is called regular if rho bar above is a Deligne-Lustig cuspidal representation. So regular, so fact is due to Kalita. Regular depth 0 supercuspidals are in 1-to-1 with GF conjugacy class of pairs s comma theta as maximally unramified maximal torus and theta a character in general position. Okay, so now these are the ones which we want to construct for self-duality. The problem is that if you if you're given so we have specific tori which we use for constructing our self-dual representations at the finite level. So we want to produce out of that an s comma theta, which continues to be um, um, regular elliptic in this sense. And so that requires some results of Kalita. So you have to choose um, an appropriate vertex. So first one does it for quasi-split groups. So suppose G is quasi-split over F, and we say that X in G, X in the building of G is super special if it is special in BG F prime for every unramified extension F prime of F. Then Kalita shows that super special vertices exist if S is maximally unramified elliptic maximal torus with associated vertex X, then this is the important thing. So this is the important property. Okay, the Weyl groups are isomorphic. So elliptic tori, they correspond to vertices in the building. So if you take their sort of the if you take their apartment, it's a point, and one point can come from many different elliptic tori of the p-adic group. And if you choose your vertex to be very super special in the above sense, then it has it is lot more in coherence with the finite reductive group uh, underlying at that point. So so we can lift information um, in a nice way from the finite reductive group underlying it. So so that is not the only thing. So our difficulty does not end with choosing the super special vertex. So I'll first state a hypothesis and tell you why we need this hypothesis. B, let SF odd be the largest subgroup of the maximal bounded subgroup of SFB that contains SF naught with odd index, then SF odd mod SF0 plus is a direct factor of SFB mod SF0 plus. Okay, so this hypothesis we will need because we um, we are given a self-dual cuspidal of the finite torus S under bar. It lifts to if you choose special vertex, it lifts to a self-dual of SF naught. Now SF naught is equal to SFB, the maximal bounded subgroup. If the if you are in the unramified group situation, um, so it lifts to SFB in a self-dual way if you are an unramified situation, but and in many other situations like simply connected and several in most of the interesting cases, but it is not always it's not clear to us is if how to do that in general. So it certainly extends to this larger thing SF odd mod SF0 plus, and from there if it was a direct command then you can trivially extend it. So that is the reason we introduced this hypothesis. So let me just state the proposition, which is the key thing which we use to prove the result. Suppose G is quasi split over F. Let X be a super special vertex in the building of G. If this this finite thing has irreducible cuspidal Deligne-Lustig representations, then GF has irreducible depth 0 supercuspidal representations. Suppose G satisfies hypothesis B if GF has such representations that are also self-dual, then so does GF. Okay, so I have already given the outline of what we am doing. So rho Deligne-Lustig cuspidal, say R under bar S theta under bar of this, then Kaleta shows that there exists a maximally unramified elliptic F torus whose parahoric SF0 is so this is anyway true for maximally unamplified tori, and where the image of SF0 in GF is SF. So um, so you lift it to a character theta of SF, and theta restricted to SF naught is just um, is essentially theta under bar, which is in general position. So it has no stabilizer in the while group, and because your vertex is super special, so the while group of the torus S is the same. The rational points of the while group of the torus S is the same. So this has trivial stabilizer, and thus theta has trivial stabilizer in WGSF, and from the pair S comma theta we obtain regular depth 0 supercuspidal. So if you are given if you know that Deligne-Lustig cuspidals exist for finite reductive groups, then by using this super special vertex, you are able to produce regular depth 0 supercuspidal. And so regular depth 0 supercuspidals exist. Now, if your representation is self rho is self dual, and G satisfies hypothesis B, then this guy is conjugate self dual by an element F necessarily of order 2, order 2, and then our hypothesis B allows a choice of S comma theta, which is conjugate self dual. So this way we so this is the broad thing in the p-adic case, that you go to quasi split group, and there using appropriately chosen vertex in the building, you can lift self dual representations of finite groups to self dual representations of the p-adic group. And then you can go to inner forms of G, and you get that they also have the same thing. So yeah, so I guess I'll complete the lecture here. I have only 2 minutes left anyway.
Thank you, Manish.
Yes.
Thanks a
So
lot, Manish.
thanks, Shripad. So any questions, Deepinder?
Let's first thank Manish for his wonderful
Yes, yes,
lectures. I
of
think this is
course.
the last lecture.
Beautiful
Thank you
topic.
very much. Yeah,
No,
can
I
ask
think
questions.
I would let others discuss. No, of course, it is quite demanding at the end.
Yeah. So yeah. So this this requires some machinery to lift this information from finite part to p-adic case. So it's not
So, eventually, for what PRD groups are you able to do?
so the almost all uh, like I left out some ramified PID groups. Unramified are covered, simply connected are covered, and um,
SL1D,
uh, yeah. So
SL1D
there is
is SL1D is not covered.
SL1D. Uh, uh, SL1D is not covered.
No, I am just wondering or asking because SL1D has no relationship to finite group theory, no depth zero, no.
Okay.
I am a bit unclear about what can be applied to SL1D.
So let me tell you. So our hypothesis is is satisfied for ramified unramified groups and those groups which split over totally wide extension of an unramified extension and simply connected groups, unitary groups.
So SL1D is simply connected.
Yeah, so simply connected group is covered. Yes. So
So it should
the
work for SL1D even though it is no split rank, no relationship to
so this
finite
thing is a
groups of
direct command. So the SF naught mod SF naught plus is a direct amount of SFB mod mod SF0 plus. So there it lifts trivially to the thing. So any representation, self dual character of the finite part, you know, it lifts to in a self dual way in simply connected groups.
again you will take n to be or even.
Uh, n to be even. Yeah, and n even we are ruling out. Yeah, of course.
So
Because
SL1D
they
will be D should have even index.
right even index. Yes. So yes. So then the super special vertex allows you to lift things.
Yeah, good, good.
Any other questions?